Units and properties, take 6. Let's jump into units and properties. So properties, there's a lot of things that we measure. Humans are obsessed with the idea of measuring things. We have basic units or basic properties such as temperature, mass, and then we have properties that build on more basic units, like we have pressure, which is force per unit area. So it kind of combines other properties where you need to know more than one thing. Specific volume, which is volume and mass, you have to know both those. Force, you have to know mass and acceleration. You have to know, in order to get to energy, you have to know what force was applied. In order to get to power, you have to know what energy was used. So all these things tend to work together in some way, shape, or form. And it's the units that we use that make all the difference, especially for when we're trying to, you get a quiz question and it's asking you to calculate the kinetic energy of a book dropped from, a book falls off the top shelf, and it's whatever book, given this amount of mass, what's its acceleration when it hits the ground? Trick question, sort of, right? Because after it hits the ground, acceleration is 0. But right at that moment, before it stops moving, like that fraction of if you could take that instantaneous moment. Anyway, let's go through a few of these properties. Let's start with one of the more basic ones, temperature. Okay? There's normally 2 temperature scales that we use, or that we talk about temperature, and we usually talk about it in either degrees Celsius or degrees Fahrenheit. Let's get a visual idea of what those mean to each other, right? So for degrees Celsius, they picked a freezing point and said, hey, let's set that at 0. Boop! So freezing point is 0 for degrees Celsius. And then somebody said, well, what are we going to pick the top of the scale to be? And they said, oh, let's do boiling. So between freezing and boiling is 100 degrees Celsius. Boiling is 100 degrees Celsius, freezing is 0 degrees Celsius. That means from freezing to boiling, there are 100 individual graduations of degrees Celsius. Okay, I can kind of see that, right? Now, the Fahrenheit scale. Well, they picked a more arbitrary starting point. They said 32 degrees Fahrenheit is freezing. Okay, well, what are we going to pick for the top? Well, let's say 212 degrees Fahrenheit. Okay, whatever. That means there's 180 individual degree Fahrenheit graduations between freezing and boiling. Okay, so the Celsius scale, between those two same points, there's 100 graduations. On the Fahrenheit scale, there's 180 graduations. That means it's almost 2 degrees Fahrenheit per degree Celsius. That gives me something I can visualize, I can understand. All right, nice. Well, both of those are on what we call a relative scale. Now let's talk about an absolute scale of temperature. So in the scientific world, they say, well, let's pick the absolute lowest possible temperature in existence as the absolute 0. So they figure out what that point is. Now, there's 2 scales, one that's associated with degrees Fahrenheit and one that's associated with degrees Celsius. The best way to remember which one is which is CK. I don't know why CK, but the 2 consonants, both interchangeable, CK, Celsius, Kelvin, right? That means the F and the R, Fahrenheit and Rankine, are together, and then Celsius and the Kelvin are together. So let's talk about Fahrenheit. So from 0 to degrees Fahrenheit, what I do is I add 460 to the degrees Fahrenheit to figure out what my temperature is in Rankine. Easy enough. So for Celsius, to figure out what temperature is in Kelvin, I add 273 degrees, which means the freezing point of water on the Fahrenheit scale is equivalent to 492 degrees Rankine. And the freezing point on the Celsius scale is equivalent to 273 degrees Kelvin. Almost messed it up myself there. This is the 6th time I've done this video, just so. One of the reasons that they developed, or that we use an absolute temperature scale, the Rankine and the Kelvin, in the scientific world, is when they're doing calculations and theoretical work, it's a lot easier to not mess with negative numbers. So every temperature from 0 to whatever in either Rankine or Celsius, or Rankine or Kelvin, are always positive numbers. There's no negative numbers. There is no negative Rankine and there's no negative Kelvin. All right, let's talk about pressure. So pressure is force exerted per unit area. Just like with temperature, we have a couple of different reference points. So similar to the Rankine and the Kelvin, let's start talking about pressure in absolute pressure, which means starting with perfect 0 as our starting point, which means there's no negative PSIA. PSIA is pressure absolute. Pounds per square inch absolute. It always starts at 0, and then as you add pressure, you get further away from that perfect 0 vacuum, the numbers go up. In fact, they go up to the point where at 14.7 pounds PSIA, we're now at atmospheric pressure. And that's where the next scale starts. That's PSIA, absolute. Now, if you take it back to our idea of temperature where there's Fahrenheit and Celsius, in pressure, there's PSIG, or pounds force per square inch gauge. And the 0 for PSIG is atmospheric pressure, which means that right now, if this was a gauge that had a reading on it right here, right, if this read out whatever pressure was being sensed here, this gauge would say 0. 0 PSIG. Because I'm not adding any other pressure to this other than atmospheric. So at atmospheric pressure, a gauge would read 0. But we know that the absolute pressure we're actually experiencing is 14.7 PSIA. Now, before I go further into the vacuum and the PSIG, PSIA, you do also need to know that there's a PSID. It's going to come up a few times in this course, and that's just pounds square inch differential. So that's between two reference points, what's the pressure difference? From a 0 to atmospheric is an absolute pressure. Now, one of the unit sets that we've talked about is pounds force per square inch. There's also inches of mercury. So from 0 inches of mercury absolute to atmospheric pressure is 29.92 inches of mercury. Now, if that number seems familiar, it's because you've probably heard barometric pressure read out, right? Hey, what's barometric pressure? Is it low? Is it high? Are we having a storm? Are we having in a high pressure system, a low pressure system? And those numbers all revolve around 29.92. 29.92 being the perfect sea level atmospheric pressure. So any variance from there shows it a lower pressure or a higher pressure. If I wanted to pick that 29.92 inches mercury absolute as and just call that 0, I have a new reference, just like pounds force per square inch gauge. I can start that, set that as 0, and then measure both up or down in either pounds force per inches squared or inches of mercury. So if I start measuring down from that 0, from that 29.92 inches mercury absolute, I am now measuring vacuum from a relative 0. Okay? And inches of mercury vacuum. If I come down to 28.92, 27.92, at 27.92, what I'm reading is 2 inches of mercury vacuum. So temperature, pressure, the confusing thing in those is what are we talking? Are we talking about a relative scale or an absolute scale? If we're talking about a relative scale, what's our zero? And are we going, are we talking about above, below? That's the kind of stuff you have to sort out. Okay, so we talked about pressure. Similar to temperature, it has a relative scale and an absolute scale. You're going to need some practice converting from one to another. So let's take a couple of quick examples. If I gave you 25 pounds gauge, PSIG, what would that be in pounds absolute? So it should be pretty easy. Remember, gauge is the relative scale, so it starts at atmospheric. The PSIA is the absolute scale, and it starts at 0. So 25 pounds gauge, up here, above the relative 0 of atmospheric pressure, we add 14.7 to that 25 pounds, and now we have the absolute pressure, the PSIA, of 39.7 PSIA. 25 PSIG, 39.7 PSIA. And then the same, let's say I gave you 25 PSIA, right? So 25 pounds absolute above actual 0. What is it in PSIG? Well, to go to the relative, to how much far above the relative, we subtract the 14.7, which leaves us with 10.3 pounds gauge above our relative 0 of atmospheric pressure. And that's our, so 10.3 PSIG is the equivalent, is the same as 25 PSIA. And you'll need to practice the same with the vacuum problems. All right. So in summary for temperature and pressure. Temperature, which measures the molecular activity, how active the molecules in a substance are, right? The more energy, the more vibration, the more energetic they are, the hotter they are, the more temperature that has, right? The higher temperature. And temperature has both relative and absolute scales, and both English and non-English units. Celsius or Fahrenheit for the relative scale, and then we have Kelvin and Rankine for the absolute scale. For pressure, we have pressure absolute, which starts just like the Kelvin and the Rankine. They start with an absolute 0, and then you work your way up. And that can be in either inches, mercury, or actually inches of water. Inches of mercury, inches of water, or pounds force per square inch. And if we're starting on the absolute scale, then it's PSIA. And atmospheric pressure is 14.7 PSIA, or 29.92 inches of mercury. And just an aside, inches of water is 408 inches of water is atmospheric pressure. All right, let's talk about mass. I'm going to read a little more from my notes here. We have to sort out how we understand mass, because here in America we mix things up a little bit, and it causes problems when we get into physics and we start trying to learn about force and mass, and we get a little confused with pounds force versus pounds mass. And part of that is because we use weight as how much mass something has, and that's not accurate. So mass is the amount of material something has, whereas weight is that amount of mass that's being acted upon by a force of acceleration, in this case, force of gravity. Gravity is the accelerational constant that is acting on a given mass. So technically, mass is a static thing. It's just how much material is present, whereas weight is a force. It's a force, and force is a mass times acceleration. Now, units of force are newtons or pounds force, which is what we're going to most commonly use, pounds force. So getting used to these conversions, 1 Newton is 0.224 pounds force, and 1 pound force is 4.45 newtons. So the biggest thing to understand about mass and weight is that mass is mass, the amount of material, and weight is a force. Now that we know the mass of something, how much material is present, let's talk about specific volume. The specific volume of a substance is the total volume divided by the mass. So if I have 1 cubic foot of something, right? How much mass, divide that by the mass, that's the specific volume. It has that much cubic feet per pound mass. Now let's talk about density. Density is the reciprocal of specific volume. While specific volume is a volume divided by a mass, the density of something is the mass divided by the volume, which means it's pounds mass per cubic feet, for example. Whatever our volume is and whatever our unit of mass is. So density and specific volume are flipped from one another. That concept will be extremely important when we start getting into your steam tables, because if you haven't looked at your steam tables yet, there's a bunch of weird little characters across the top of those columns. One's like a small V. The one that's missing is none of those talk about density. Your steam tables don't take into account density. So if I give you something in density, you will need to convert to specific volume in order to use the steam tables, and then oftentimes you'll do a calculation and then have to convert with the steam table and then have to convert back to density in order to get to the whatever I'm asking. So the easy way to remember to convert between specific volume and density, since density is mass over volume and specific volume is volume over mass, the specific volume is 1 over density, and density is 1 over specific volume. So this is a good time to talk about intensive and extensive properties. Intensive properties are independent of the amount of mass, whereas an extensive property varies directly with the amount of material or mass present. So let's say I take a quantity of stuff and I divide it into 2 equal parts. The intensive property, right, for example, the specific volume, the volume per cubic foot, or the density, the cubic feet per pound mass, is the same in both. That hasn't changed. But the extensive properties, for example, the volume or the mass, have changed. So temperature, pressure, and specific volume and density are examples of intensive properties, right? If I take 4 pound mass of some material and I divide it at 400 degrees Fahrenheit and I divide it into 2 pieces, they're each at 400 degrees Fahrenheit, but it's half the mass and half the volume. All right, I'm going to just read from this. Specific volume is the total volume of substance divided by the total mass, whereas density is the total mass divided by the volume. Intensive are independent, right? Intensive, independent of the amount of material present, the mass. Extensive properties are dependent on how much mass. They vary directly with the amount of mass. So when we're talking about all these properties, whether it's density, volume, mass, temperature, we're talking about properties of a system. And how we define that system, especially when we're talking about power plants, is important. We can be talking about systems at a very smaller level, down to even a component level, like what's happening inside of a component, inside of a pump, inside of an air ejector, inside of a heat exchanger, could be considered our system. Or we could be broaden our perspective of a system and talk about how this pump and this heat exchanger and this tank, along with all the piping and all the valves, all work together as a system. However we define that system, there are different types. A closed system means that it's always working with a fixed amount of material. Material in many cases is fluid. We pump fluids through cooling systems, feed water systems, and if it's a closed system, that same mass of fluid is always staying in that system, and it just circulates. Examples of closed systems in your car, right? Your cooling system. Even though you've got an expansion tank, even though you can fill it, it's normally a closed system, right? The radiator cap's on, your expansion tank cap is on, and it has coolant in it, hopefully half water, half coolant, and your pump, your water pump circulates that coolant through your engine and the radiator, and it's that closed system, it just stays in there. The difference between a closed system and an isolated system is that an isolated system, what we mean by that is that there's no interactions with the environment. No work done on or by the system, no heat absorbed or given off by the system. Realistically, it's not something we encounter, right? It's not something we can build and show you, here's an isolated system. But we do talk about isolated systems in an ideal world when we're talking about thermodynamics. Because when we're building a system on paper, we need to make it a little simpler for ourselves. And so talking about an isolated system can simplify some of the dynamics of what's going on. Then we have an open system. Open system should be pretty obvious. It means you've got a reservoir, and out of this reservoir you got a pump, and it's pumping water to some other thing, right? And rainwater makes up the reservoir. That's an open system. It gains or loses mass to or from its environment. A smaller example of an open system would be a compressor. Gas, so if I have a cylinder and I put gas in here and it moves the cylinder, right? It's adding something to it, it's an open system. Okay, so there's some terms. I'm just going to read these off the computer here. There's some special terms in your PowerPoint and in your text. You do need to understand these, though I'll help guide you. Isothermal, constant temperature. So an isothermal process. We're going to talk about Charles Law and Boyles Law, and you'll have to figure out which one of those is an isothermal process and which one is an isobaric process. Isothermal, the temperature is held constant. Isobaric, the pressure is held constant. So those two are important, isothermal and isobaric. Adiabatic means no heat flow to the environment, so it's not giving off any heat to the surrounding environment. We've already talked about isolated. Isochoric, the volume is held constant. The isenthalpic means the enthalpy remains the same. And isentropic is the entropy remains the same. So we simplify how we talk about thermodynamics. If I want to convey an idea or look at what a system's doing from just one perspective, I make some assumptions, and maybe I'm going to assume that this cylinder is expanding, but we're going to maintain a constant temperature. So it's an isothermal process. Maybe I'm good describing some other system, and I want to ignore any heat given off to the environment. So we call it an adiabatic. We just assume it's adiabatic, and we talk about the system that way. All right, so for units and properties, we've talked about temperature, pressure, a little bit about force. We talked about the difference relative versus absolute. We talked about the different types of systems. So pressure is pounds, is some pressure per unit area, right? and we have open systems, closed systems, and we have to have a way of measuring pressure. So let's say I've got this system. It doesn't matter whether it's open or closed, it's a pipe. And from previous classes, you should have talked about differential pressure across something like an orifice. So if I have that pipe and I put a plate in it that's got a hole drilled in the center, that causes a back pressure on one side. If the flow is going this way, the pressure builds up on this side. There's a pressure drop across that orifice, and the pressure's lower on this side. So now imagine that pipe, and I take, and below that orifice, I take a tiny little tube and I connect one side to the other across that orifice plate. Well, because this side is at a higher pressure than this side, if I fill that with water, that little tube with water, the water levels are going to be different. The water level on the higher pressure side is going to be lower because it's going to be pushed down by the higher pressure, which displaces water on the lower pressure side. So one of the things you'll see in your student text and in the exam bank, the NRC exam bank links I gave you, is something called a manometer. And that difference in pressure is being measured across an orifice using a column of water. And so it's a visual representation of what's happening with pressure and the difference across it, and applying it to stuff you learned from a previous class. The reason pressure is so important in our course and in nuclear power in general is because we use it to determine, we can learn so much about a system. We can learn, knowing what pressure something's at, we can figure out, well, how much water is in there. We can calculate, we can figure out if we know the temperature, we can figure out what density is. And that's going to be important for when we're doing pump theory and trying to figure out, well, is this pump going to cavitate or is it not going to cavitate? What's the suction head? Does it have enough water? Is it dense enough? But we have different ways of measuring these properties in a system. And you'll see in your text we have board-on tubes, diaphragm type pressure detectors, level detectors. It uses these different properties of the system and how it behaves with pressure and temperature and level and volume and density, and all these things play into what information can we get out of this system. So I mentioned that in the scientific world we often convert from degrees Fahrenheit and degrees Celsius to our absolute scale of temperature, which is the Rankine and the Kelvin. One of the examples of why that matters is when you're dealing with gas laws. And two of the ones we're going to use are Charles's Law and Boyles Law. Brooklyn Nine-Nine, Charles Boyle. Anyway, so Boyles Law says if the temperature remains constant, the volume of a given sample of a gas varies inversely with the pressure of the gas. Written out, what that means is the pressure times the volume, the pressure initially and the times the volume initially is equal to the pressure final times the volume final. So if pressure goes up, one of those other two in the last have to go up. For example, if volume decreases, pressure increases. That makes sense, right, when you're compressing a cylinder. For Boyle's Law, we treat it as an isothermal process. Remember in our special terms that isothermal means no change in temperature. So it's done for convenience sake because we know that physically there will actually be a temperature change. But in order to study what happens, what the relationship is between pressure and volume, we basically assume no temperature change, isothermal process. Now, Charles's Law, similar, says under constant pressure the volume of a given amount of gas varies directly as its Kelvin temperature. So another way of saying that is the volume increases as the temperature increases, or temperature increases as the volume increases. So Charles's Law is an isobaric process. We assume no change in pressure. So while for Boyles Law, we assume no change in temperature so that we can study the relationship between pressure and volume, for Charles' Law, we assume no change in pressure so that we can study the relationship between volume and temperature. And the interesting example in my notes here, so the way it's written out is the initial volume divided by the initial temperature is equal to the final volume divided by the final temperature. Nice simple ratio setup equation, right? Well, if I gave you the problem 1 cubic foot of gas at 100 degrees Fahrenheit and 1 atmosphere is heated to 135 degrees Fahrenheit. Knowing that applying Charles' Law, so no change in pressure, what is going to be the final volume? Well, if you don't convert the temperature, the 100 degrees Fahrenheit, if you don't convert it to Rankine, then you'll end up with 1.35 cubic feet. But if you do convert it to Rankine, you end up with the correct answer of 1.06 cubic feet. We have talked about pressure, we've talked about a bunch of different properties, right? And these things get used to figure out the state of a system on a larger scale. Hey, I got this tank of water and it's got a pressure gauge at the bottom of the tank and the pressure gauge reads blah. Whatever that pressure is gauge, PSIG. Okay, so knowing that, I only need to know one other thing. If I know temperature, well, then I can figure out what the density is, or I can figure out the height of the column of water, or how much water's in the tank. I can figure out its we haven't talked about potential and kinetic energy yet, but there's a lot more we can figure out. So we use these as measuring devices to help us understand the state of our various systems. Oh, an important and an interesting note on the temperature scale stuff. So generally here in the United States we use degrees Fahrenheit. However, for our nuclear power plants, sometimes we have upgrades that we've done over the years, and these upgrades are purchased. They're more modular in nature, and they're purchased as a generic thing from a manufacturer somewhere that works for most plants. So we're a boiling water reactor, and a place built a thing called an isophase bus duct cooling system, which allows all the nuclear power plants to get a little more megawatts out of their generator. Okay, we cool the big heavy wires coming out, and now we have more megawatt production. Well, this isophase bus duct cooling system was created in the UK. So all of its stuff is in degrees Celsius. We don't convert all that, right? We buy the thing as a unit, install it in the plant. So we do have some things that show Celsius, while most of the stuff is in degrees Fahrenheit.